Welcome to the Orientation Explainer for Case Study 07. Over the next couple of hours, you're going to be working through this on your own. My goal right now, it's just to make sure you're oriented, focused, and really thinking about the problem before you write a single line of code. So, let's dive right in.
Let's start with a concrete engineering scenario. We're looking at a mobility network today, specifically a sample of morning commute flows on Boston's Blue Bike system. Now, when you look at the raw data, you might notice really heavy ridership between high-income areas. Naturally, the immediate question an engineer or a city planner asks is, does income actually shape who rides with whom? Like, is there a real structural socioeconomic pattern here? Or do high-income people just happen to live near the busiest transit hubs? We absolutely have to know if this observed network pattern is just happening by pure chance, or if it's a legitimate structural feature of the system.
And that brings us directly to the core professional skill we're building in this case study: infer. You need to test claims with permutation against the right null model. Now, the everyday alternative most analysts reach for first: vanilla regression. But here's the catch. When your observations are connected in a network, that standard independence assumption fails, and it fails silently. Edges share nodes. Nodes share neighborhoods. Standard error formulas are just wrong by default here. You simply can't just run a regression, look at the p-value, and trust it. You've got to use network-aware inference.
So, how exactly do we do that? Well, we start on paper. Put down the keyboard, step away from the IDE, and grab your notebook. Because before you even open the interactive tool, you're going to complete a sketchpad exercise. Drawing physically forces the concept into your head before the syntax can hide it. You're going to draw 5 neighborhoods, color code them by income, draw the expected heavy edges, and then sketch out 2 null distribution histograms. Let me walk you through exactly what that's going to look like.
Just imagine this evolving right there on your physical page. You're drawing 5 distinct nodes for the neighborhoods. You mark the high-income ones in amber and the low-income ones in indigo. Okay, now, relying strictly on your own domain knowledge of how a morning commute actually works, you'll draw heavy arrows indicating where you predict the heaviest flows are going to go. You are predicting the structure.
The absolutely crucial point here is this. The actual thinking, that happens on your sketchpad. The interactive tool in your browser is strictly there for verification. You really can't draw a network that you don't fundamentally understand. And once you've got the logic mapped out by hand, the actual computation basically just becomes an execution step rather than a frustrating guessing game.
Okay, let's move over to the interactive playground and see how this all builds. Once you open the lab, you're going to run into the core tension of this entire case study: choosing the correct null model. Network inference basically asks, given the structure of this network, would this pattern arise just by chance? But random with respect to what, exactly? Well, we have 2 options. An unblocked permutation shuffles labels across all the nodes, completely ignoring any community structure. A block permutation, on the other hand, shuffles labels strictly within community bounds, which preserves that underlying geographic structure.
Think about the physical constraints of our engineered system for a second. In learning check 02 of the lab, you're actually going to run these permutations. So picture a hub-and-spoke geography that has fixed docking capacities. Is it physically plausible for an unblocked null model to just randomly swap a massive 280-ride commuter weight onto some tiny casual recreational route?
Well, I'm definitely not going to spoil that learning check for you. You'll figure that out yourself when you run the simulation and see exactly what those unblocked permutations actually do to the network.
After you wrap up the interactive lab, you'll move right into the coding exercise, where you'll compute these statistical distributions on real data. And whether you choose to work in the R playground using iGraph and dplyr, or you take the Python track using NetworkX and Pandas, the underlying logic is exactly identical. You're going to be calculating the observed assortativity and then comparing it directly against your generated null models.
But before you start typing any code, let me leave you with the single most important takeaway from this entire module. If you fit the wrong null model, you will get the wrong answer with absolute total confidence. I mean it. An unblocked permutation will tell you that basically anything is statistically significant if the neighborhoods are already demographically segregated. It actively lies to you. You have to control for the inherent structure of the system you're actually engineering.
And that brings us to your final task before you dive into the module itself. Turn to a fresh page in your notebook for this sketchpad prompt. I want you to substitute your own project network, the one you're analyzing for this course right now. Draw 5 to 15 nodes. What is your specific grouping variable? And based on everything we've just discussed, which of the 2 null models, unblocked or blocked, is the right one to test your question? Pause here, draw it out, commit to an answer,
and then go open the lab. Because in network science, the system structure ultimately dictates its survival. So ask yourself, are you measuring the real system or just an illusion of your own making?